Okay, so the next problem up on the docket is problem 75. Write the Kekulé structure for each of the following compounds. So we have 6 of these problems to do, and we can probably knock them out relatively quickly. So first problem we'll do is problem A. We've got this compound CH3CHO. So first problem to address is the CH3 bit. So just as a very quick reminder for this carbon, what this is saying is that this carbon has 3 hydrogen atoms attached to it covalently. So for all of these, whenever you see Kekulé, it's kind of implying to depart from this old method of drawing carbon-hydrogen bonds like so, like this right here. So before, you might have drawn, specific hydrogen atoms and carbon atoms like this. So then this carbon right here would be attached to another carbon, which might be this guy right there. Okay, so this is fine. It's nothing. There's nothing wrong with it. It just turns out later on, this kind of explicit drawing of carbon is very slow. It's clunky, and it doesn't look as elegant as drawing implicit carbons. And what implicit carbons means is that you have carbon not as a formal C. So the way that you would draw this out, or the way that I would draw this out, if I wanted to draw a CH3 or a methyl group, is not with the carbon formal bond hydrogen, is you just represent that carbon as a single point in space. Okay, and so what I'm going to do is I'm going to go ahead and make that carbon-carbon bond between this carbon right here and this carbon right there. Okay, so I'm going to make, here's carbon 1 and here's carbon 2. Okay, so if we were going to draw it out up here using a kind of Lewis formality, you would have the first carbon, then the second carbon, and then the big problem here, the big challenge is to figure out what the heck this structure is with the hydrogen and the oxygen. So the first thing you have to remember is that, well, this carbon is not being drawn as if it had a charge, and so because there is no charge drawn out, you have to assume it's neutral. And then that means that you have to remember that, well, the only configuration where carbon is actually neutral is if it has 4 bonds to it, either 4 single bonds or 2 single bonds and a double bond. But as long as it has 4 covalent bonds in some way, shape, or form. So we know that this carbon is attached to a hydrogen right here, and we also know that it's attached to an oxygen. So we know we have that right there. So right now, this carbon only has 1, 2, 3 formal bonds to it. So there's nothing wrong with it, but at the same time, there are a couple of things that are wrong in that, well, one, carbon's octet is not filled, which should immediately set off some alarm bells in your head. So right now, we know we have 2 ways of fulfilling carbon's octet. The first way is if we added 2 lone pairs. So if we added 2 lone pairs right here, we'd have 2, 4, 6, 8 total electrons around that carbon, but unfortunately if you do your formal charge calculation, that formal charge is going to be, 4 minus, 2 lone pairs, or 2 electrons in the lone pair, and we're going to have 3 covalent bonds. So 4 minus 2 minus 3 is going to equal -1. So that would imply that that carbon would have to have a negative charge on it. And we know that that's not the case, because if it was the case, we'd have to draw it up here in some way. Okay, or overall, we would have to imply that the molecule as a whole was negative. Okay, and that would be fair game. But right now, we know that overall the molecule is neutral. So unless you want to make that carbon negative and try to make something else positive, then we're going to be out of luck. Okay, so this just seems like a bad avenue to go down. So the easier way to get around this is just, to give this carbon an extra bond. So right now, making a double bond between this carbon and this oxygen is totally legitimate because right now we have, a total of 8 electrons around this carbon. So if we do our formal charge calculation again, we've got 4 minus 4 is going to be equal to 0. So that, yields a neutral charge on that carbon, which makes sense because the whole molecule as a whole is neutral. Okay, so the other thing right here that we want to do is to make sure that this oxygen we want to recognize how many lone pairs are actually around this oxygen, because right now, if you don't draw them out, it's later on you can kind of assume that they're there, but to start off, it's probably a good practice to draw out all of your lone pairs, just so I know that you know what you're talking about. So right now, if you didn't draw any lone pairs and you didn't assume that you had lone pairs, this oxygen would have really wacky charge. So the other thing is that you don't have any kind of octet being filled for this oxygen. So if we're going to fill up the octet for this oxygen, we'd add one lone pair here and one lone pair here. Okay. So now if we want to calculate the formal charge for this oxygen, you know that oxygen has a valence of 6. So we start off with 6. And then we subtract the total number of electrons that are lone pairs, so 2 and 4. So we're going to say 6 minus 4. And then we're going to have 2 formal covalent bonds. So that's going to be 2. So 6 minus 4 minus 2 is going to be equal to 0. Oxygen's charge is 0. Overall, the molecule is 0. So everything seems to be working out. Okay, so everything works out here for the carbon, and everything works out here for the oxygen. Okay, so this is the carbon right there. This is the oxygen right there. Okay, so I guess I kind of backtracked for a second, but this was going back to if you wanted to draw out all of your atoms, and once this is an okay way of figuring out a general structure. But again, it's good for you guys to try to get away from drawing out explicit carbons and explicit hydrogens, unless you really, really have to. Unless you really want to call attention to something, best to stay away from this. Okay, so the faster way of doing this, in the Kekulé type way, is to draw everything condensed. So we basically don't draw hydrogens unless we really have to. We don't draw carbons unless we really have to. So a better way of doing this is, again, I'm just going to draw that carbon as a single point in space, and I'm going to attach it to another carbon, which just turns out to be another singular point in space. Okay, and so now this carbon right here, let's call this carbon A, and this is carbon, I don't know, this is let's call this carbon B. So this is carbon B. So this is carbon A, this is carbon B. Okay, so carbon A is here, carbon B is here. We know that carbon B has to have a double bond to an oxygen, and so let's go ahead and do that. So this is carbon B. We're going to draw both of those covalent bonds to the oxygen explicitly. So here we go. So this is your oxygen. So this is carbon B. So now this is one of the scenarios for carbon B where it's probably good to go ahead and draw out that hydrogen, this guy right here. So let's go ahead and draw him out, just to make sure that I know that you know that there is only one hydrogen attached to B. Okay, so if we're dealing with this functional group, do you remember what it's called? Take a second, see if you can figure out or remind yourself what the functionality of this functional group is. I'll give you about 2 seconds. Pause it if you want to. So hopefully you found out that this was an aldehyde. So whenever you're drawing an aldehyde, it's probably best to go ahead and explicitly draw out these hydrogens, so just so you don't lose track of them. Okay, but if you notice over here for carbon A, I'm not even going to draw any hydrogens on carbon A, and that's totally legitimate. In fact, and I'm going to get rid of this A and B nomenclature just to make it a little bit cleaner and neater, but if I was going to draw or draw out molecules in an exam and I wanted to draw out this, this aldehyde, I would draw it preferentially as this. So one of the challenges whenever you're trying to adjust to this new drawing motif is for you to recognize that on this carbon right here, you have to recognize that that carbon has 3 implicit hydrogens still bonded to that carbon. They're there, but I'm just not drawing them out. Okay, and this is actually a bit that confuses students quite a bit. So one of the challenges is for you to be able to almost instantaneously recognize how many hydrogens are attached to a carbon. So you have to go through this mental tick list every single time. And it takes a little bit of getting used to, but overall it's a pretty trivial task. And so that reason it's really good, but at the same time, if you're not used to it and you don't do it all the time every day, you're going to have a lot of trouble remembering how many hydrogens are attached to a carbon. So best for you to get used to this kind of nomenclature. So I'll be drawing everything in this kind of condensed form from now on. Okay. All right, so let's do problem B. I'm going to go through problem D a little bit faster. I'm going to stick with just this kind of condensed Kekulé notation. So for B, we have a CH3 group, and then you have an oxygen and another CH3. So I'll go ahead and draw our first carbon just as a point in space. So this is our first carbon right here. This carbon is attached to an oxygen. So this carbon is carbon A. Let's call this carbon carbon B. So this is carbon A, and somewhere along the line we'll have to add carbon B, but we know that carbon A has 3 hydrogens, and we know that carbon has to have 4 total bonds. So again, I'm not going to draw out all 3 of these guys. They're going to be attached to carbon A, but I'm just not going to draw them out. So this carbon A has 3 hydrogens attached, so then we have to make that 4th bond, okay, to make sure that that carbon is neutral. So what's really happening is this carbon right here is attached to this oxygen. So carbon A is going to be attached to oxygen, and that oxygen is then going to be attached to carbon B. Okay, so carbon B right here. And again, I'm not going to draw out any of the hydrogens that are attached to carbon B. Okay. One thing to keep in mind, just to make sure you're okay with it, is to make sure you are cool with the fact that this oxygen up top, right here, doesn't have any charge. So overall, again, we know that because, at the very beginning, we would have to say whether the molecule as a whole has some kind of charge on it. And since the molecule overall is neutral, that means that, this oxygen has to have 2 lone pairs. So we have to have a lone pair here and a lone pair here. So again, that oxygen's formal charge is going to be its valence. So that oxygen's going to have a valence of 6, always, always, always. Then we're going to subtract 2, 4 electrons in the lone pair, and then we're going to subtract those 2 formal bonds. So 6 minus 4 minus 2, again, is 0. And again, this formal charge calculation is super, super simple. The hinge kind of, it depends on you being able to remember how many valence electrons a particular atom has. But because of the fact that we're only really ever interested in hydrogen, boron, carbon, nitrogen, oxygen, that you really only have to memorize a handful, but it's really important that you know all of the valences of all of these very basic, first row atoms. Okay, so anyway, let's go ahead and I'm gonna, delete these letters. So just to overall draw the molecule, this is going to be our final molecule right here. So this guy it has a specific functional group name, and I'll give you a second to see if you can figure out what the name of this guy is. We probably would have talked about it in class by now. If not, it's coming up pretty soon. Okay, so hopefully you found out that this is called an ether. This is called dimethyl ether. And we'll talk about specific naming principles later on. Okay, so overall not too difficult. Alright, so let's do part C. Part C is, again, we have a CH3 or a methyl group, and then that methyl group is attached to a carbon, and then we have 2 oxygens and then a hydrogen. This bit might be a little confusing if you haven't seen this before. But overall, this is part and parcel. We've done this, or we'll be doing this many, many times. So if you see the CH3 group, another way to abbreviate this is ME, or methyl. So we saw that kind of in question 74. But again, the ME is going to be your methyl group. Okay. So again, I'm not going to draw out these hydrogens explicitly. They're going to be totally implicit. It's going to be faster. So this is carbon A, and say this is carbon B. So I'm going to do A, B, and then, so this is carbon A. We know we have 3 hydrogens attached here, and then we've got, carbon B up here. Actually, I'm going to erase that, move that down low. So it's going to be carbon B. And so carbon B right now only has 1 bond to it. And again, overall the molecule is neutral. So if we make something charged, we're going to have to balance out that charge in some way. Overall, that's a pain in the neck. Best to try to make everything neutral right off the bat, just to make things easier on ourselves. Okay. So basically what we need to do is we need to figure out how to make 4 more bonds to carbon B. Okay, so we already have 1, B to A, and we're going to take those up with these other 2 oxygens. So carbon B, this is very classical way of drawing out this functional group. So this carbon B is going to have one attachment point to one of these oxygens. We can call this oxygen 1, and it's going to have another attachment point to another oxygen. We'll call that oxygen 2. Okay, so 1 and 2, 1 and 2. Okay, so don't be fooled here. This is not saying that these two oxygens right here are attached to each other. They're not. There's no formal bond between these two oxygens, oxygen 1 and oxygen 2. And indeed, they're both attached to that carbon B. Okay, so right now what we've done is for this oxygen 1, overall, again, let's try to make everything neutral. So we're going to make 2 lone pairs on this oxygen. It's going to make it neutral for the same reason that this oxygen was neutral, right here. Okay, and so now oxygen 2, we have to figure out a way to make that neutral. So we have to do that by using up this last hydrogen right here. So the way that this, kind of elongated, condensed, drawn out, written out way is implying is that you have a bond between this oxygen and this hydrogen. So instead of having 2 lone pairs, we're going to have 1 lone pair taken up, and right here, we're going to have 1 lone pair taken up right here, and we're going to have another lone pair taken up right here. And so now, instead of having a double bond between an oxygen and a carbon, we're going to use 1 single bond between this oxygen and the carbon, and the other single bond between this oxygen and this hydrogen. Okay, so now we've got our overall molecule constructed, and again, I'm going to make it pretty. I'm going to get rid of all of these labels just to make it a little bit easier to see. Okay, so now we've got oxygen, and this also has 2 lone pairs, so it's going to be neutral for the same reason that this guy over here is neutral in the yellow. And so this carbon right here is also going to be neutral because we have 4 covalent bonds to it. Okay, we may or may not have talked about the functional group of this molecule, but I'll give you a second to try to find it. And then I'll give you a name. Okay, so hopefully you found what this guy is called. This is called the carboxylic acid. We may have talked about it in class, but if not, again, we'll talk about it soon. Okay. All right, next up on the list is D. So what we have here are, we have a methyl group, but what these parentheses are saying is that we have a methyl group, but we have not just 1 methyl group, we actually have 3 methyl groups. So a shorter way of drawing this might be to say, okay, we have a methyl group and we have 3 of those. And we also have another carbon with an oxygen and a hydrogen. So this looks kind of similar to problem C over here, but the only difference is that now instead of having 2 oxygens, oxygen 1 and 2, we only have 1. Okay, so we're going to have to figure out something to do with that. So really at this point we can either make potentially a carbon-oxygen double bond or a carbon-oxygen single bond. So pause the video and play around with both and see if you can figure out which way is the correct way to do it. So again, pause the video, try it on your own before you listen, and then I'll give you the correct answer. Okay, pause the video. Okay. Okay, so now I'm assuming you have a structure in mind. You've unpaused the video, and I'll go ahead and draw this guy out. So right now I'm going to center everything on this carbon right here. And so what we're going to do is we're going to draw 1, 2, 3 bonds, and then a 4th bond right here. So we're going to have 3 bonds to a methyl group and 1 bond to an oxygen. That's the way I'm going to do it. So I'm going to have 1, 2, 3, 4 bonds, and this point in the center again. Remember that represents a carbon. Okay, so again, we're not going to draw it explicitly, but it's definitely there. It's still a carbon atom. Okay, so what we have is we have a methyl group, 1 methyl group taken up, 2 methyl groups taken up, 3 methyl groups taken up, and then we have this last bond. So you have basically 2 more atoms to deal with, an oxygen and a hydrogen. So oxygen is going to go here, hydrogen is going to go here. Okay, so again, overall, the overall charge for the molecule is 0. So the way you can deal with that is, again, add the 2 lone pairs for the oxygen. And again, sometimes you will see them, lone pairs drawn out for oxygens explicitly. Sometimes you won't. So in general, actually, whenever you read in the book these lone pairs will not be here. So sometimes these lone pairs are actually explicit, but if you know that the molecule is neutral, then you know that those lone pairs must still be there. So it really depends on who's writing it and what the context is. So, um, so, so why is this the correct answer? Why do we not have the alternative? So I'm going to erase this guy. And the other alternative we could have had was you could have had this carbon in the middle, so let's call this carbon A. And I'll get rid of these other two arrows just to make it a little bit prettier. So why does carbon A not have a double bond to an oxygen? Okay, and I guess I'll get rid of the carbon, the explicit carbon, just to be consistent. And the easiest reason is just for the following, that we know we have to have 3 methyl groups. So let's say we have a methyl group here and a methyl group here, and we have to take care of another methyl group, so right here. And then we also have to take care of a hydrogen right here. Okay, so first things first, let's take care of the major issue with this problem. By now we've probably talked about carbon and its inability to expand its octet. So what this means is that you cannot break the octet rule for carbon, which basically says that you can't have any more than 8 electrons surrounding a carbon at a time. So if you count how many electrons are actually surrounding this particular carbon, we're going to have 2, 4, 6, 8, 10. So we're going to have 10 electrons surrounding this carbon, which is overall a very bad situation. Okay, well, tier right there. Okay, also, so this is the main issue. So this is actually an impossible configuration. And the second bit is that also, if this was correct for some miraculous reason, if you did a formal charge calculation on this oxygen, you would get something other than neutral. So pause the video and see if you can calculate the charge on this oxygen right there. Okay, so this oxygen is going to have, again, the way you calculate this is you do the valence of the oxygen, which hopefully you remember as being 6. It's a very important number. You need to memorize that number. So oxygen is going to have a formal or a valence of 6. So 6 minus 2 lone pairs, and then we're going to have 1, 2, 3 formal bonds. So 6 minus 2 minus 3 is going to equal plus 1. So what this means is that this oxygen, as drawn, technically has a plus charge on it, which is impossible because we already know, or the way that the problem has been presented is that this molecule is overall neutral. So this is wrong for so many reasons. Wrong, one, because of charge, and the second is wrong because of the violation of the octet rule. So that's why this way of drawing is completely wrong. Okay. Next up on the docket, let's do problem E. I'm just going to speed through these last two. By now, it's probably getting a little mundane and redundant. So I'll go through these pretty quickly, and I'm going to make very little commentary. But if you have questions, feel free to ask. So we have this big guy right here. So it's carbon A, B, C, and D. Okay. So this is going to be carbon A. Again, hydrogens are implicit. Carbon B, in this case, I'm going to draw out the hydrogen just to show you where everything's going. So there's going to be one hydrogen here. So this is carbon B. And right here, we're going to have carbon B attached to carbon C. And so right now, to make sure carbon B has all, its octet filled, we're going to have 4 bonds to it. We're going to take that up with the last OH. Okay? So carbon C, and then carbon D. So this is going to be carbon D right here. Okay, so in this case I am going to draw out this carbon explicitly just to make sure we see where everything's going. So this is carbon D. We're going to have 1, 2, 3 bonds to a nitrogen. Okay, so right now this carbon has, or carbon D, has 1, 2, 3, 4. Its octet is filled. Overall its formal charge is going to be its valence, which is again 4. So 4 minus 1, 2, 3, 4 covalent bonds. It's going to be neutral, which is great. And again, overall, this molecule is neutral. So in order to do that, we need to address this nitrogen right here. So thinking of that, we can make this nitrogen neutral very easily by just adding a lone pair. And so now you have to remember the valence for this nitrogen is 5. So it's going to be 5 minus 1, 2, 3 bonds, formal bonds, and then minus 2 electrons that are lone pairs. Okay, and so now 5 minus 3 minus 2 is 0, and everything checks out there and there. Okay, so overall, I'll go ahead and get rid of the lettering just to make it nice and pretty. Okay, and this would be a very nice, totally acceptable way of drawing this molecule E. Okay. All right, and then finally, last but not least, problem F. Let's go ahead and label all of our carbons. So A, B, C, D, E, F, G. Okay, so overall we've got 1, 2, 3, 4, 5, 6, 7 carbons. So I'm just going to make a big old carbon chain. So A, B, C, D, E, F, G. So A, B, C, D, E, F, G. So this is actually, you see how this is much faster than drawing out carbons explicitly? I can just draw one big long chain and then just tack it on from there. Okay, so the thing here is that this carbon A, we actually have 2 of them, so let's call them A, and they seem to both be attached to carbon B, so it's going to be A, and let's call this guy A prime. Okay, and so we're going to take up this last bond to carbon B with this hydrogen right here. So this guy is a hydrogen. Next up we have carbon C. It's going to have, let's go ahead and get rid of this actual label, put it on the other side, just to make it easier to see. So this is C, and C is going to have 1 hydrogen, so there it is. That's the hydrogen I just drew. And it's also going to have another, methyl group right here. So this is your Me. So actually it looks like I made a mistake, so let's go ahead and go back and erase a couple of these labels. Okay, so now what I'm going to do for carbon C is I'm going to put that methyl group on there. So this is going to be our carbon D, so I'll say D. Okay, and in this case it actually might be a little simpler to go ahead and draw out the Me, just to let your audience know what that is, and then I'll label it D. Okay, and so now the way that this is drawn now is that C is going to be attached to E. So we're going to have E right here. This is our carbon E. So next up we have carbon E attached to carbon F right here. And carbon F is going to have not 1, not 2, but it's going to have 3 methyl groups attached to it. So first things first, let's change this first group from an ethyl to a methyl. Okay, and then let's add 2 more. 1, 2. So this is methyl, this is methyl, and this is methyl as well. So again, all these are methyl groups, and so this is methyl G, this is G prime, and this is like say G double prime. Okay. One bit to note is this parenthesis can be a little tricky. You might have to go through a couple permutations just to make sure that you don't get stuck. So, if I had tried to attach D directly to C, it would have quickly become apparent that we couldn't tack on E to it. Just because we would have run out of space, we would have had to make a Texas carbon, something like that. We would have tried to, break oxygen's octet or carbon's octet, which wouldn't have been a good thing. So let's go ahead and get rid of this ABC nomenclature just to make it a little bit nicer to see. Okay. So, and I'll go ahead and add a methyl here and a methyl here. So this is methyl A and A. So let's say this is A and this is A prime. Okay, and we know there are 2 here because of this 2 right here, and we know there's only 1 on D because there's no subscript here, and we know that for methyl group G there are going to be 3 of them because of this guy right here. So this is going to be the G prime, and the G double prime again. Okay, so this one's a little bit difficult, but it might have taken like 1 or 2 tries just to get it completely right. But overall, this is going to be the form of this molecule. Okay, great. All Alright, and on to the next problem, which I believe should be problem 77. Okay, great.